A pristine, scientifically flawless invention is rarely enough to guarantee a company's survival. The physics might be perfect, but the business can still shatter. Look at this typical founder's notes. They see superior efficiency in the lab, look at the great data, and immediately decide to start a company. This treats the invention as a scientific trophy rather than a commercial product. This blueprint illustrates the inevitable outcome: building a magnificent scientific cathedral sinking into a financial swamp because the ground was never validated. Contrast that with an engineered system resting on solid bedrock, a foundation built on validated assumptions and operational repeatability. Commercial survival demands treating deep tech not as a romantic quest, but as a rigorous, engineered architecture. The framework to manage this complexity is computational thinking. It is a structured, algorithmic approach designed to pull deep tech out of the lab. This system diagram highlights the core reality. Profitability is a multivariable problem. Science and engineering are only two gears in the mechanism. They must physically mesh with manufacturing, customer needs, economics, and strategic timing to drive the system forward. Many ventures collapse because they fail to force hidden assumptions into the open. Variables like expected yields, adoption speed, or expected price premiums remain vague and untested until it is too late. Explicitly identifying and testing these variables is the only way to transform an abstract scientific phenomenon into a durable, revenue-generating commercial system. Let's test this framework with a hypothetical scenario. Suppose a team develops a new OLED material. In the lab, it demonstrates superior efficiency and a significantly longer lifetime. This schematic shows the necessary system override. Instead of immediately selling the material, we reject the non-computational reflex and initiate a rigorous logical sequence to stress test the invention. This diagram illustrates the first phase of commercialization, a sequential testing gauntlet to evaluate baseline technical viability. At the first gate, scientific validity, we prove the improvement is robust across batches, not just a lab anomaly. The second gate checks device integration. The material most function inside commercially relevant device architectures. Moving to the third gate, manufacturing compatibility, we demand hard proof that synthesis can maintain purity and yield at commercial volume. Ignoring these manufacturing constraints at this early stage guarantees a catastrophic operational emergency later on. The final gate in this phase asks the most critical question: economic value. Does this technical improvement actually reduce costs or enable a premium device? Surviving this technical gauntlet merely qualifies the invention to exist outside the lab. It has not yet proven it has any actual market value. This computational filter visualizes a harsh truth. A deep tech breakthrough has absolutely no commercial meaning until it is explicitly translated into economic value for a specific user. This reveals the mindset gap. The metrics that impress scientists, novelty, theoretical limits, raw efficiency, are rarely the metrics that drive market adoption and final profit. This KPI translation matrix serves as a tool to cross that gap. Looking at the top row, if efficiency improves by 5%, we have to ask, does that meaningfully increase customer value enough to drive a higher market adoption rate? On the second row, if material lifetime doubles, does that lower replacement frequency enough to justify premium pricing? Finally, if manufacturing yield rises from 60 to 85%, how does that alter the gross margin trajectory and improve overall unit economics? Without this strict translation matrix, teams will inevitably burn capital optimizing features that are technically impressive but commercially irrelevant. Translating technical variables into economic realities acts as a safeguard. It prevents a company from engineering a marvel that nobody will actually buy. This diagram shows our stress-tested OLED material moving into the second phase of the gauntlet, market reality. The first gate is customer segmentation. We systematically determine the optimal beachhead market. Is the initial target smartphones, automotive displays, lighting, or wearables? This flowchart outlines the next critical decision. The go-to market pathway must be dictated by a cold analysis of constraints, not romantic ideals about building an empire. If the company holds strong patents but lacks capital for large-scale manufacturing, the logical route is licensing IP. If the technology requires tight integration across materials and process engineering, the math demands vertical integration. And if adoption barriers are extremely high, demanding immediate trust and distribution, the bottom path shows the necessity of forming a joint venture. Founders often want to own the whole stack because it sounds heroic, but the spreadsheet is unsentimental, and it will ruthlessly punish irrational choices. Only then do we arrive at the final gate, profit logic. This demands a clear view of gross margins and the working capital required for revenue. Successfully entering the market is an algorithmic deduction based on your specific capabilities and constraints. It is never a leap of faith. Computational thinking is far too important to be quarantined inside the technical R&D department. This diagram illustrates it as the universal API. It acts as the shared translation layer routing logic between the scientists in the lab, the operators in the market, and the finance team at the spreadsheet. This architectural floor plan details how that shared language structurally synchronizes workflows across the entire enterprise. You can follow the data streams. Engineering performance thresholds inform manufacturing scale-up protocols, which then directly feed into finance models mapping the path to unit profitability. Organizations utilizing this closed-loop system eliminate friction. They operate with vastly shorter learning cycles and superior capital allocation. This bridge blueprint reviews the entire commercialization journey. It is a rigorous, deliberate sequence of steps, not a sudden leap across a chasm. We start by taking an interesting phenomenon and verifying a mechanism that creates measurable performance. We then prove that this performance solves a real problem and develop a solution that can be produced at scale. Finally, we reach the apex, confirming the production model supports healthy margins, resulting in a durable, profitable business. Profit is not magic. It is structured value capture under extreme constraints. Embracing this algorithmic reality is how we drag deep tech out of the lab and into reality, with far fewer delusions along the way.